So with no further ado, we'll move straight in. Our first presenter this afternoon is Caitlin Rowett, Senior Technical Services Manager at Hillgrove, to give us an update on Kanmantoo, a productive year.
Thanks. I'm here to talk to you about what we've been up to in the last year. Since we presented last year at SAEMC, we've had a pretty big time of it and actually gone into production. So as a bit of a background onto the Kanmantoo deposit, we're located 60 kilometres from the Adelaide CBD up the southeastern freeway in the southern Adelaide Hills. And we're in a region that's been a significant copper district for a long time, with original mining back in the 1840s, with a mine active on our site between 1846 and 1874. The first open pit on the site was ran in the 1970s, and then Hillgrove commenced exploration in the early 2000s, with the open pit commencing in 2011 and running through to 2019. Once the open pit finished in 2019, we started a resource drill out with the aim to head underground. And the resource drill out went so well, we commenced in May 2023 our development underground in earnest, and then we started stoping in December 2023 as well. So the Kanmantoo deposit and the geology really drives a lot of the decisions we make and how the technical style and how we mine. So a bit of background on the geology is the copper gold mineralisation is hosted within a complex shear corridor, and the host rock is part of the Kanmantoo group sediments. These are high in biotite, andalusite and garnet, and the fluids have utilised the shear corridor, resulting in the resulting thermal conditions and fractionation of the fluids have resulted in the alteration we see on the site. And this is what's led to the emplacement of the copper-gold mineralisation. The chalcopyrite is the copper-bearing sulphide for all of our deposit, and we also see some pyrrhotite occurring in that mineralised corridor. As a result of the shear fabric, mineralisation typically forms lensons and veinlets of chalcopyrite and pyrrhotite, and the complex shear system has resulted in the variations in the orientation of the mineralised shoots. The main lithologies that we see on site are based around the alteration styles that we see and how much alteration they've experienced. The three most common ones we observe are the biotite schist, characterised by a really strong foliation, and the biotite dominant fabric. A garnet andalusite biotite schist, known by our operators as a tic-tac rock, because it looks like everyone threw the tic-tacs into the rock from the andalusite crystals. And this is a good indicator for when we're getting closer to the mineralisation, as the andalusites become poikilbastic and create a ghosted kind of texture. And then where we have our mineralised zones, we see the biotite garnet chlorite schist. This is characterised by banding of the chlorite and garnet and the coarse sulphide veins. Pretty much all other lithological units that we see on site are a variation of these three, and just as a basis of whether there's extra minerals or less minerals across all of the areas. Our mineralised shoots have a natural level of cut-off grades based on the type of mineralisation we observe. The density of the S2 controlled copper, that really drives our mineralisation between 0.2 and 0.4. And then our epigenetic sulphide veins really, when they start to increase in frequency, start to drive it between the 0.4 to 0.8. And then once we see over 0.8, we see our stockwork brecciated zones, where we see our coarse mineralisation. These coarse brecciated zones are our harder to predict because of their stockwork nature, and the geometry and continuity becomes harder to predict based on our drill spacing. Whereas when we're within the corridor, we can really well predict that alteration corridor. Our underground operation has really flourished in the last year, and we are now another 150 metres vertically below the Kavanagh pit, and we've actually commenced development out towards our Nugent lode as well. Our system is all set up with jumbo development for all of our access to levels. These are on a 25 metre level spacing. We're using long hole open stoping for our bulk production tonnes, and we have both transverse and longitudinal stope access, allowing us for our bogging capacity. We have really good geotechnical conditions, and which has meant that we don't have to have any backfill based on our numerical modelling, but that does mean we can have really wide, long and striked stopes, and at the moment we have some up to 50 metres wide by 100 metres along strike and up to 75 metres wide, and they're going well. So I wanted to focus today on some of the projects that we've done to be able to achieve these things that we're doing in the underground operation. And some of the key technical projects that we've focused on in our first sort of 12 months of operation have looked at things to do with geotechnical, engineering and geology. Our geotechnical one was really looking around our deep support. So looking at self-drilling anchors, utilising of resin for cable bolts and SDAs as spiling bars. In the engineering side, we've had to look at how does our foliation in the fabric of the rock assist in our drill and blast design. So we've looked at drill pattern design, how does the drill holes deviate, and then we've looked at other programs like being a new mine, being able to establish Wi-Fi underground to allow for environmental monitoring, real-time plod collection, and then really these opportunities are endless with the Wi-Fi underground. Geology side, we've looked at how do we set up our grade control systems, and we've really lent into using the spectral scanning to determine our face grades and then utilising that back through the rest of our grade control system. We've also been using XRF of our grade control core and building on the system that was established during the open pit. Whoops. So the three that I'm going to be focusing on today are the resin installation of cable bolts, drill hole deviation and our spectral scanning. So when we mine a wider span, we do need to support the de-stress zone, which is often longer than our usual split sets or friction bolts that allow. This is where typically cable bolts are used, or we've trialled out SDAs. To use the SDAs or the cable bolts, it's the connection between the grout or the resin that really creates the significant portion of the strength of that bond. And so we've looked at a couple of different ways to do this. So we tested our SDAs, which was a self-drilling anchor, which had a sacrificial drill bit on one end, and then you can couple as many of the rods together to create the length of the bar that you need. This is a bit different to normal. Most places would be utilising a cable bolt, and we ended up going back to cable bolts but using the resin that we were testing with the SDAs. We preferred the cable bolt because it gave us the longer embedment, but the resin really assisted us in being able to have a fast turnaround on installation. So normally with grout, you need to wait 24 hours before you can fire the cut below, whereas with the resin, it cures instantly once the two parts are mixed. So it meant we were able to gain 24 hours back into our mining cycle. We still had the same connectivity between the bolt and the rock mass, and then by going back to the cable bolts, it meant that we had the high tensile strength. It had more of shear capacity as well than the slightly more rigid SDAs. So that really helped us in refining a traditional mining method but making it a little tweak to make it work for us. Another project that we've worked on significantly is utilising the information we gained during our resource drill out on our drill hole deviation. While we were doing that resource drill out, we could determine which way the holes would swing based on how it was cutting the fabric. And we were able to produce these diagrams that showed us which direction holes would move, where they'd stay steady, so in relation to the angle it was cutting against our mineralisation. This is then also continued in our underground operation. We see it in our blast holes and we see it in our development cuts as well. The image on the left there is some of our drill holes that were scanned using a bore track following drilling by the production rig, and we can see that they sort of lift and move off to the left. This is quite a repeatable pattern we've now been able to establish. So once we've been able to establish that pattern, we've actually refined the way we do all of our drill holes, adjusting the collar positions to make sure that the burden and spacing is continuous up the entire stope, and particularly the rises, and we've been doing the same thing in our development. The image on the other, with the voids there, is the same stope once it was fired. Once we'd utilised this drilling information, we were able to refine the process so we could actually extract the entire mineralisation as designed with the adjustments in the collar and still achieving the burden and spacing as required. In the geology space, we've been really building our grade control, the systems from scratch, and building on systems that would be common to many. We've really lent into the use of hyperspectral information and the scanning of all of our underground faces using a infrared along with a LiDAR scanner that is mounted on the back of an LV. It has used calibrated algorithms that have been calibrated to the rocks on our own site by scanning over 1,000 trays of core to make sure the model is calibrated to what our rocks look like. The fact of our simple mineralogy of the chalcopyrite does assist us in this process, and it allows us to collect detailed information in a really quick turnaround because we can process the faces within 45 minutes of being back in into Wi-Fi reception, and that's really just limited due to our current Wi-Fi connection. It's repeatable and it can be done by anyone. So we have a suite of a team of mine technicians who actually do this predominantly, and then they provide the information back to the geologists who make the decisions on what the classification of each of those headings are based on the scan. This is an example of the imagery that we get from it. The RGB image shows us the face. We see the mineralisation. The AL203 image shows us detail of the rock mass. Because our rock is aluminium rich, we can see the remnant bedding, we can see how that's been infiltrated by the fluid systems, and then we can overlay that with the copper image, and we can see the distribution of copper, which is based on the distribution of chalcopyrite in the face. The more we do, the more we can keep scanning all of the images. We can start to build up level by level information. So here's a couple of levels that we've scanned and started to build up all the information across an entire end. We can then use this to help define our stope boundaries. So here's an example of how we define some of the stope boundaries. We have an AL203 image on the left there, and we have the copper image on the right. Looking at the dark blue on the bottom right-hand side of the AL203 image, you can start to see where the remnant bedding has actually been disrupted by the fluid flow. By noticing those patterns, you can actually start to build up boundaries, turn them into wireframes within our usual 3D modelling softwares, and use that to then build up your stope definition boundaries. Another part to the spectral scanning is that from the copper image, we can actually turn that into a region of interest and turn that into a copper grade each face. So this then becomes part of our real-time monitoring of all of our development headings. We can then determine where those material moves. Does it go to the waste dump? Does it go to the ROM? Where on the ROM should we put it? And we can do that within a shift instead of waiting for a traditional face sample, which often will have to go to the lab and has normally a 12 to 24 hour turnaround, so you lose it on a shift by shift basis. By using the LiDAR scanner, we also collect information on the geotech of the drives. We can start to pick up structures, and by coupling this with the spectral scanning, which identifies the different minerals on the joint planes, we can actually start to build them up level by level. Here's an example of the same stope from earlier, when we had the faces from the level above and below, and we started to build up all the joints in green there and start to link them up. As we've continued developing and got more levels online, we can now start to build up which ones are continuous, where they are, and how they all link together. So for us, the key benefits of the unit have been the fast turnaround time of new information, our unbiased collection of data because we're not putting interps into our maps, straight away. It allows us to do it in a timely fashion. It's repeatable. It can be done by anybody. It's an easy-to-use system. And the copper grade estimates of each face allow us to be dynamic in our distribution of copper and selection of what material goes to the ROM. In summary, for us at Hillgrove, 2024 has been a really big year. We've done lots of projects, including these ones, and on top of doing resource extensions, mineral reserve estimates, all of the, and having our maiden underground reserve. But these key projects that we've been working on alongside that has really built on traditional underground mining methods and adjusted for the geological conditions that we see on site. It's incorporated new and emerging technologies and found ways to utilise them in our system. And because of that, we're really looking forward to 2025 as we keep learning and keep growing and developing our systems. Thank you.